Hello, everyone. Welcome to Quick Disconnects for Liquid Cooling, Design, Specification, and Implementation. My name is Elizabeth Langer. I'm the R&D Engineering Manager for the Thermal Business Unit at CPC, or Colder Products. I'm also an active member of the OCP Advanced Cooling Systems Cold Plate Workstream. A little about CPC: we design and manufacture connectors for a variety of industries and applications, and specifically here specializing in quick disconnects for thermal management and liquid cooling of electronics. The goal of the presentation today is to provide a high-level understanding of the current state of liquid cooling technology in the industry, benefits, methods, and key considerations for successful implementation and reliable deployment. And then, of course, quick disconnects being an integral component of data center thermal management, we're going to introduce and discuss some of the fundamental considerations for designing and optimizing quick disconnect performance in cooling systems, touching on materials of construction, chemical compatibility, valve design, and pressure loss should provide a good baseline to help enable engineers during the specification process. So why liquid cooling, and why liquid cooling now? We've seen with advancements in semiconductor technology over the years, shifts in power consumption and consequently associated cooling requirements. But now in recent years, we're yet again in a place where compute power and certainly densities have reached the limits of efficient thermal management with traditional air cooling techniques. Now that liquid cooling is becoming more widely considered, data center and colocation providers can begin to realize a number of benefits in the form of energy savings, improved power usage effectiveness metrics, PUEs, cost savings, the ability to dramatically increase densities at the rack and server level, and noise reduction. If you've ever been in an air-cooled facility, you know the fans have a significant impact on the working environment. Within OCP, there's been quite a bit of activity over the last few years to educate and develop best practices across the industry around liquid cooling technologies for data centers. Here we have the liquid cooling architecture scoped by OCP ACS. Goal here being to facilitate architecture harmonization to promote accessibility, consistency, and reliability. Interesting to note is the intent here that these technologies are not mutually exclusive. On a case-by-case basis, a facility might require one over another, or potentially a hybrid approach, implementing multiple cooling technologies. For example, a rear door heat exchanger in tandem with a direct contact cold plate structure. Supporting the ACS architecture are a variety of subsystems and components that are critical to successful and reliable operation of the cooling system. The components themselves, as well as interactions and dependencies between them, warrant detailed analysis during design and specification. Considerations for coolants should be the addition of corrosion inhibitors, potential addition of anti-biofouling agents. Considerations around viscosity and specific gravity will certainly lend themselves to the next component, which would be pumps, leading to the pumping power capacity, reliability, and redundancy of the system. Manifolds, heat exchangers, cold plates will all have requirements around operating flow rates and pressure, regulations and guidelines around filtration, debris, material and compatibility, and then certainly tubing and quick disconnects will bring with them a host of separate considerations. Point being that every component within a liquid cooling system matters, so it's important to think holistically and early throughout the design process. Within a data center facility, typically there will be two fluid circulating loops with a CDU barrier between them. So on the facility side, there might be fewer connections, large plumbing and fittings to support the high volumes of fluid that need to be circulated throughout the cooling tower and chiller. And on the technology cooling system side, or TCS side, where the IT equipment resides, ACS architectures such as the rear door heat exchanger, cold plate, and immersion will utilize many more connections and require more detailed consideration around the specifications. The closer to the IT equipment, the more critical the QD's performance and reliability becomes. In the upper right here, we have an example of possible connection points for an ACS rear door heat exchanger or cold plate server. There could be connections at the manifold, at the rear door heat exchanger inlet and outlet, on the blade chassis level itself. Now, with an understanding of where quick disconnects might be installed within a data center and the importance of their performance and reliability, especially as they get closer and closer to the IT equipment, we can dig in a little deeper and understand some of the key parameters of importance for specification. When thinking about the anatomy of quick disconnect, we can identify 3 high-level categories for consideration when selecting the right QD for a specific application. Material selection is a very important factor to consider early on, both from a structural and mechanical viewpoint, but equally important with regard to chemical compatibility, ensuring that all wetted materials that will be in contact with the coolant, as well as other component materials within the loop that may have an interaction. Understanding of and visibility to various configuration options related to mating and mounting will enable designers to fully optimize the performance, as well as provide flexibility in promoting usability and serviceability of the system. And finally, valving and shutoff characteristics of the quick disconnect are really imperative for designing an efficient and reliable system. Quick disconnects can be comprised of a variety of materials, metals and polymers including engineered thermoplastics as well as elastomers, can be effective really in any combination. When we think about metals for quick disconnects, we want to consider the alloy, the base alloy itself, whether it's brass, aluminum, or a stainless steel, and as well as properties of that particular alloy. Is it corrosion resistant? Is it going to be strong? Surface treatments of metal QDs are also important. That could be a nickel chrome plating on a brass quick disconnect. It could be a heat treatment. It could be an oxidative passivization or anodize process. For plastics, we want to consider mechanical strength, chemical compatibility, flame retardants, hydrolytic and thermal stability characteristics, as well as all of the performance characteristics that we see listed below. In addition to the structural characteristics, it's important to understand other physical characteristics such as chemical compatibility, corrosion, and erosion. So coolant compatibility is important, especially with regard to elastomeric seals, which can be very susceptible to swelling or hardening or oxidizing if exposed to the wrong temperature or coolant chemistry. We want to ensure that all materials within the wetted fluid loop are compatible with the coolant itself and with each other due to the fact that there might be interactions that may take place. Galvanic corrosion being one of them. If, for example, 2 metals are present in the same conductive fluid loop that are on opposite ends of the electric potential scale, for example, aluminum and copper, you might experience some catastrophic galvanic corrosion. Another consideration with regard to material and flow rate is flow path erosion. There are recommendations and guidelines around maximum fluid velocities based on the material and the diameter of the fitting or tubing that the fluid is flowing through. And certainly another consideration is always environmental. So humid environments, if there's salt, if there's debris, those can all affect the reliability and performance of the quick disconnect. Many quick disconnect configurations exist on the market and can be often customized to fit the unique needs of an application. The level of configuration can take a variety of different forms. For instance, the mechanism by which the quick disconnect is joined. So it could be a blind mate versus a hand mate. Blind mating being advantageous if the operator is not intended to interact with the quick disconnect. It might be buried farther into the system or on the back of the server blade. Handmate might take the form of a ball and sleeve style connector or a thumb latch style connector where the user would need to be able to easily access it during installation and service. Valving and shutoff could come in the form of either a flush face non-spill valve where there's a minimal wetted surface on connection and disconnection, or it could be a wet break where maybe the quick disconnect is installed in a location where there's a little higher level of tolerance for a little bit of spillage or drip. And certainly termination. So having the flexibility as a designer to spec in a quick disconnect with a hose barb or a straight thread or taper thread or some other unique style termination will certainly add to the performance and reliability of the system. Alongside manifolds, tubing, piping, cold plates, quick disconnects are really a key consideration when analyzing a flow network model. They can have a critical impact on the overall cooling system flow and pressure loss. So if you're from more of an electronics background, I think sometimes it can be helpful to consider the hydraulic analogy, where we describe some considerations for optimizing fluid flow to components of an electrical system. You consider voltage, we can liken that to fluid pressure, where we're directly relating a capacity and ability to do work. Electric current can be likened to fluid flow rate. How fast can we do that work? We know that the rate of heat transfer is directly related to the mass flow rate. So in theory, higher flow means more heat can be moved. That being said, it's not always practical from a system efficiency and safety standpoint to simply increase the pressure and flow. And so careful analysis up front of the impact of the quick disconnect on overall system performance is crucial. Additionally, as we see on the right-hand side, and from our friend Bernoulli, we can understand the relationship of fluid velocity to fluid pressure. As the fluid velocity increases, for example, when flow through tight spaces and small fittings and orifices, the fluid pressure will actually decrease, contributing to the overall system pressure loss. And vice versa, as the flow path becomes less restrictive, the fluid velocity will decrease and pressure will stabilize. This concept is fundamental to understanding and being able to optimize flow paths within quick disconnects to produce the least possible pressure loss across the set. A nice way to characterize the fluid flow and pressure loss of a quick disconnect fitting is to use the flow coefficient, or CV. CV value is a dimensionless coefficient that correlates the volumetric flow rate, or gallons per minute, to a 1 psi pressure loss. You can see below we have an equation here where Q defines the volumetric flow rate as it relates to the CV, the delta P, or pressure loss, as well as the specific gravity. It's interesting to note that a lot of times the published and cataloged CV rating for a quick disconnect is typically reported with water, and the specific gravity of water being 1 can be a little misleading when you're analyzing for pressure loss of fluids that maybe have a higher viscosity or higher specific gravity. So in those cases, we can use correction factors and correlate the CV to the appropriate coolant that's being used. Now that we've got a handle on the anatomy of a QD, I want to introduce some of the key functional requirements. Spillage is certainly a consideration, especially as we're getting closer and closer to the IT equipment, and we can quantify that in cc's or milliliters as the volume of fluid upon disconnection. So every time you make and break that disconnect or that quick disconnect pair, there will be an appreciable amount of fluid buildup either on the QD or in the form of a droplet. Inclusion is kind of the opposite of that, where it's the volume of air that's actually introduced into the fluid loop on connection of the QD set. And this could be problematic if a large volume of air is introduced into the system every time a connection is made. That might lead to some adverse effects in the cooling system itself. And of course, leaks, unintentional fluid discharge, which could potentially be catastrophic, especially if the coolant being used is a conductive fluid and falls on those highly sensitive electronic devices. Some ways to mitigate and enhance seal efficacy and reliability are to deploy multi-lobe seals versus standard O-ring profiles, or redundant protection against sealing and leaks in quick disconnects. Temperature is an important consideration from a reliability and stability standpoint over time. We want to consider operating temperatures as well as any storage and shipping temperatures that might be exposed to the quick disconnects. Flammability, of course, we have UL 94V ratings where we want to consider all materials exposed to the cooling environment meeting this requirement. Examples of plastics that might be used in environments that are inherently flame retardant, not using halogenated flammability additives such as bromine or chlorine are definitely considerations. Conductivity, specifically with regard to thermal conductivity of metal quick disconnects, can be an important consideration when thinking about user and operation safety. And chemical compatibility, as we discussed earlier. Wetted materials and the fluid loop should all be compatible with the coolant and with each other. And this will really help ensure long-term service and reliability. In summary, we covered a lot of parameters and considerations to take into account when specifying a quick disconnect for a cooling system. We really want to make sure that all system requirements are locked in place or at least understood prior to specifying a quick disconnect. We have guidance from the Advanced Cooling Systems group, specifically the cold plate workstream, in the form of a white paper, which we're referencing a table here that can serve as a checklist. And then we want to make sure that we're engaging with experts early, and that could be experts within quick disconnects or manifolds or tubing. It's always good to ask questions early on. Thanks for attending. Hopefully this presentation provided some valuable insights to use when specifying quick disconnects for liquid cooling. If you want to get involved, there are various work streams through OCP and specifically the Advanced Cooling System group. You can follow the links here below to get involved. For questions or more information, feel free to reach out to me. My contact information is below, as well as my colleague Barry Nielsen, who's an applications development manager. We're happy to answer any questions you might have or discuss any topics that might be interesting to you. Thanks. All right. Hey, everybody. Thanks for attending. Hopefully some good food for thought there. Maybe learn something new. Got quite a few good questions that came in throughout. Feel free to add some more, and we'll try to get through as many as we can here. Got the first question here. What is the best way to test the performance of a fitting? That's a really good question, and I wish there was one simple test to rule them all, but in reality, it's a combination of things and really depends on the application and what associated risks might be present there. But for data center and HPC applications, I suppose on commissioning at the system level or prior to shipping, it might be common to perform some leak and pressurization testing. There's industry standards that are kind of starting to converge on a 3x safety factor for testing relative to expected operating pressure. And with regard to leak testing, there are standards available to qualify leak tightness via maybe a bubble leak method or a gas leak test method with helium or maybe a nitrogen blend. But prior to all that, one thing you can do is reach out to your QD supplier and ask for a validation report. So this is something that CPC does, and it's a very comprehensive test protocol and report that will cover the whole gamut of performance for the fitting. So it might include mechanical performance testing, such as force to connect, side load strength, cycle testing, some thermal performance for high and low temperature scenarios that might be to cover shipping and preconditioning environments or high temperature environments that might accelerate some things. And then of course flow and leak testing. Got another question here. You said that quick disconnects needed to be taken into account early in the application development. How early do you mean? That does sound like something I would say, and I think there's opportunities for multiple touch points throughout the application development cycle to consider the quick disconnect. So at the beginning, maybe as you're doing your flow and thermal network modeling, it's important to consider things like what the equivalent hydraulic diameter of the QD might be that you need, what's the anticipated threshold for pressure drop. And then once you move more into structural and mechanical design, then it's important to start to consider things like the latching configurations. Do you want a thumb latch, ball and sleeve, blind mate connection? What terminations might you want? Is it going to terminate to tubing or hose, or is it going to be threaded into a manifold? And certainly materials, and that's definitely going to be a key factor for determining material and chemical compatibility for the system. And then, of course, as you're working through risk management mitigation, reaching out to your quick disconnect suppliers for those validation reports and really having deeper discussions with them about the specifics of your application will really help to vet out any risks or obstacles to ensuring the successful implementation. I've got a good question here. Is there a CPC website where you can either buy direct or browse the connector descriptors? Um, Certainly there is a website, and I'm hoping that maybe my marketing colleague Barry's on the line. He can add that in the chat section. And the link to the website where we do have options to buy direct through CPC as well as a variety of channel partners that are available to help you drill down into exactly the right solution that you need. So thank you. That's a good question. Next one here. Fittings seem like such a minor component in the overall system. Do you have some examples of what has gone wrong or could go wrong if the quick disconnects are not specified correctly? That's a good question. So one thing that I would see often as a failure mode once a quick disconnect is implemented is often related to material incompatibility. So an example I can think of, not necessarily in a data center environment, but in a similar cooling loop application where an aluminum quick disconnect was used with a copper cooling loop that was flowing DI water. Someone grabbed the aluminum quick disconnect wanting to save some weight over a stainless alternative, but knowing the DI water is always thirsty for ions, and certainly in the presence of the copper, the QD ended up acting as a sacrificial anode to the more cathodic copper components and eat all the way through the wall of the thread. So that's an unfortunate example of how something can go wrong, but often can be averted by engaging again with quick disconnect suppliers early on. In that example too, while stainless might have been a great potential solution, pun intended, plastic could have also been a great option as they needed to cut some weight out of the module. So that's something to consider there. Other examples of what might go wrong in a quick disconnect deployment in a data center could be related to debris and contamination, and that's where guidance around filtration comes into play, and that could be at the CDU level or elsewhere in the environment. Certainly want to consider that on initial commission, maybe flushing the system to make sure you're getting any debris that might be present from the manufacturing processes, get those out of the cooling loop. Got another one here. What sort of volumes would I need in order to develop a custom fitting solution? So I don't know if marketing is on the line, but I'll go ahead and I'm inclined to say anywhere from 1 to infinity. So in all seriousness, it's going to depend on the complexity of the design and the ask. But I think in reality it's possible to do anything from a small volume, short run to high volume, large scale production manufacturing. So a custom fitting might entail anything from a different elastomeric seal compound, so identifying a seal that's going to be compatible with whatever the coolant media so that it doesn't swell or deteriorate over time, to a specific machine thread. Maybe there's a custom port that you need to tap into your manifold or system, and anywhere up to a fully unique ground up design and purpose-built solution to fully optimize your system. That said, the point that I'd underscore there too is to don't let the QD be an obstacle to your system innovation. Engage QD experts early on and just collaborate, see what's possible. That's what's kind of fun about this OCP community. There's not really any wrong answers or wrong ideas at this point. We've got a lot of different backgrounds and perspectives in the community, and it's fun to see where we can take that into advancing quick disconnects options. So let's see, to avoid corrosion within the cooling loop altogether, what are your recommendations? So again, that's going to be reaching out to certainly your quick disconnect supplier, but also your coolant suppliers and maybe any other component suppliers, just to really establish a comprehensive wetted materials list. And by that, I would mean materials that are going to be in contact with the coolant and indirectly in contact with each other. So we talked a little bit about galvanic corrosion earlier. And so ensuring that all the materials on the wetted material list are compatible with each other is going to be the first step. And then as it relates to corrosion, looking for things, not having metallic components that are far apart from each other on the electric potential scale. And then also certainly materials like thermoplastics and elastomers that are going to be compatible with any coolant, specifically dielectrics or fluorocarbons. That's kind of a good segue into. I got another question here about how does CPC qualify chemical compatibility. And another one as one that is there a quick disconnect that's designed for compatibility with fluorinated fluids. So such as we've got some trade names here, and I think 3M's got some discussions too on Fluorinert and Novec later in the day. What we would do there is, again, start with the wetted material list, so looking at all the materials of construction for the quick disconnect, and identifying ones that might be at risk with exposure to the coolant, as well as considering thermal situations. So while one material might be compatible with a fluid at room temperature, at elevated temperature, it might start to degrade or see some crazing effects. So that's something that we would qualify and kind of establish a wetted materials list for certain coolants. As new coolants come in or are presented to us by customers, that's something that we can work with the customer to test for compatibility, typically with an accelerated immersion test at various temperatures. So that's a really good question. A question here about the number. What's the number of insertion, connect, and disconnect cycles that you test to? So there are some industry standards around that. Typically, it's going to be in the 1 to 5,000 range. CPC, we actually test up to 10,000 make-break cycles, and then after those 10,000 cycles, would perform a functional test for leak and mechanical functionality, just to make sure that the quick disconnect hasn't been compromised. So that's certainly an interesting question. 10,000 quick disconnect cycles might be beyond what you'd expect in a data center environment, but one thing that helps us understand might be accelerated failure mechanisms and modes. So stress testing them in that way is a really good thing to do. Maybe time for one more here. Are there any materials or coolants that you recommend we stay away from? I don't think that there's any that I would want to say that you should stay away from. It's more about really understanding what coolant you are using and what materials it's going to be in contact with. So, again, if it's going to be a water in contact with metal, then you want to understand, the corrosive capacity of that. Maybe that includes adding some corrosion inhibitors and biocides, surface treatments to any metal components you're using, like nickel plating the brass or passivating the stainless. And then as we move into some of these, newer dielectrics or HFEs, understanding the chemical makeup of any thermoplastics or elastomers you might be using, watching out for certain plasticizers or additives that might be extracted into the fluid. So I wouldn't say that there's any materials or coolants that you should stay away from. It's really about just understanding the ones that you do have and any interactions that might be present between them all. So I got a follow-up question to the cycle test. If there is a failure after 10,000 cycles, what does that failure look like, and what components fail the most? That's a good question. I'd say that typically the failure mode isn't going to be anything structural or mechanical, really. Typically it's going to be associated with wear of the elastomers. And so that's something where lubricant definitely comes into play, and that could be a lubricant that's added to the elastomer on assembly, or it could be the lubricity of the coolant itself. And so that's primarily related to, the cycle rate of the test, and, the speed and friction that's associated with that. But really, really good question. I think with that, we maybe were able to get through everything here. So really appreciate everybody's time, and hopefully you got some good information here today. Again, if you've got any other questions or want to bounce an idea off of us, definitely reach out. Enjoy the rest of the summit. Thanks.